Okay, good afternoon. So this is lecture 6 and some announcement. We have uploaded the assignment 2 and the deadline is 7th of February, which is right after the Chinese New Year holiday. Okay, so assignment 3, if we do it, if we don't have this Chinese New Year interruption, we will be uploading this assignment 3 this weekend. But because we have a little bit of time, so I will release it a bit later. So just focus on assignment 2, and the deadline of this is a week after this. So it's a weekly assignment. So you can expect this deadline to be on the for some of you maybe the most important day of the year, and it's a Monday, 11 o'clock. Okay, and I recognize the difficulty to do online teaching and to do to learn online, and therefore I've decided to release the video. Okay, so somebody should see whether this video works well. Okay, so if you have if you have difficulty, just email me. Okay, so this is the video from Monday is already there. At least I checked this morning. It seems to be working on my terminal, but somebody should check. Okay, and the exercise classes will be held on Zoom. No choice. This is as expected, but I would like you to be careful. The TAs will use a different link. Okay, so the link you are using now is my link, is my room, is my Zoom room. So they are not able to run it from my room. And all the one-click links are available on Blackboard very prominently. So you should be able to get all these links without problem. Okay, so this is a bit of housekeeping. Do you have any question? There's a question, but I don't understand. So assignment 2 has been uploaded. This is a question about assignment 3. Assignment 3, it will be about some of the questions you can do already. Okay, so if you want them, you have it well, let's say this weekend. Okay, so you can focus on assignment 2. So this should not interrupt your Chinese New Year holiday. Okay, so now you can work on your assignment 2, and you can have your break next week. And assignment 3 technically is for the week 4. You should work on assignment 3, and you will cover the material from this week. Okay, so that is what I want to say. So do you have a problem with this deadline? Is it inconvenient for you? You know who you are. Do you ask me about this assignment 3? I can easily set it to 15 if you like. Okay, I don't hear anything. I don't see any more typing on the chat, so I will just assume there's no problem with this. Okay, so let's begin the lecture. So last time we talked about some engines. We started to talk about some engines. One of the most important engines we talked about was Carnot engine, which is based on Carnot cycle. So this is something we will use a lot and a lot today. I don't want to repeat. I don't want to write everything again. So I will just show you the slide where we introduce the Carnot engine. Sorry. Here. So basically, what I wrote here in red is the description for a Carnot engine. So Carnot engine is an engine based on Carnot cycle, and in addition to that, this engine is reversible because all the segments are reversible. And then we also only want to operate this engine between two reservoirs, only two reservoirs. Okay, and later when we go to more reservoirs, we can try to generalize it and get some theorems that are useful for thermodynamics, and that leads to the discovery of entropy. And we will indeed take advantage of our knowledge of Carnot engine. Okay, so right now you need to keep in mind, for the purpose of this lecture and for future lectures, make sure you keep in mind that Carnot engine is reversible and operating between two reservoirs only. Okay, so and now last time I told you the second law of thermodynamics is very frequently stated in some kind of very interesting ways. Like, for example, I told you there are two statements here, and these are really the statement of the second law. Okay, and they can be formulated in this diagram. And we stop here. We kind of stop here. And now basically, I gave you Kelvin's statement and Clausius' statement. So Kelvin's statement tells you you cannot have an engine like this. Okay, so simply put, you cannot. Now there's a symbol here that tells you this picture is not possible. Okay, you cannot just extract heat from the hot reservoir and then convert everything to work 100% efficiency. This is not allowed. And this one basically tells you you cannot extract heat from the cold reservoir and then transfer everything to the hot reservoir. Okay, so these two are two different statements of the second law, and they are of course equivalent. And later, I think you can already appreciate this. Right? If we write it like this, there will be another statement which is in terms of efficiency. Right? You can define an efficiency for a heat engine, and that efficiency will tell you something, will say something about it. And that something has to be consistent with the second law. Okay, so my aim today is to prove this for you. So I'm going to prove only one direction, and then you will do the other one in assignment 3 actually, and that will allow you to establish the equivalent. So what I mean is I'm going to do now, to prove that these two statements are equivalent. You need to start from, for example, you start from not C, and then you lead to not K. Okay, and then you can do not K, and you go to not C. Okay, and if you can establish two directions, it means these two are equivalent. So this is not K, is equivalent to not C. Okay, and this is kind of simple but very cool, and you might have seen it before. So I'm going to do one. I'm going to give you. I'm going to do number 1. Okay. And in my note, of course, I also give you number 1, and you will do number 2 yourself. So let's add one. So let's add one more slide. Okay, how do we do this? How do we do? How do we go from not C to not K? Okay, the way we do this is no. I want to get the engine first. Where's the engine? Where? How did I do this before? There's a cute way to. I will just copy. Okay, I'm going to put two engines side by side. Okay, one I'm going to call it not C, because this is the one. This is the one that I want to start. Right, I want to start with not C. Okay, so I'm going to label everything first. This is Q2, and this is also Q2. There's no point to do Q1, Q2 anymore because there's nothing else. So everything has to respect the first law. So all the heat energy you get has to be transferred. Okay, so this is not C, and I'm going to do a process like this. Okay, so listen carefully. I'm going to put another engine between the same reservoirs. Okay, and this engine is an engine which is allowed. Okay, so this is in my note I call it a normal engine, which is a heat engine, which you know very well. You know is allowed. And as a normal engine, a standard engine, you can do something like this. You can take heat from theta 1, the reservoir with higher temperature, and then you can extract work W, provided that you dump some heat to the thermal waste. Okay, so in this notation, my W is Q1 minus Q2. Okay, so some heat is wasted. Otherwise, this difference will be converted to work. All right, so now I already write it like this. I already write it this way. Now, just assume I should have technically I should use Q1 prime, Q2 prime, and this is W is Q1 prime minus Q2 prime, right? But I can always adjust the rate of my engine. I can run it a little bit differently, such that for one duration I can control how much heat I can extract from Q1 and how much heat I have to dump into theta 2 proportionally. Okay, so that's to say I can always adjust everything such that I want my Q2, everything, all the heat that is rejected by the normal engine to be consumed by the engine not C. Okay, so in this case, I can set these two to be the same. All right, so once I do it this way, look what happened. All the heat will go to the cold reservoir and then come back through this. So this is kind of meaningless now, because in this case, if I arrange it this way, what will happen is the following. I can view this as a composite engine. Okay, so now you can see I begin to have some disaster here. So if I view this whole thing as a composite engine, like this, this is my composite engine, which means this is like a black box. So all the heat, as far as the composite engine is concerned, Q2 becomes internal. Okay, I might as well just say there's no Q2. All right, so you reject some heat and then you consume some heat energy. So this is equivalent to not having any Q2. So I can draw the composite engine like this. So this is the composite engine. So as far as the composite engine is concerned, I don't need to draw Q2 anymore, but I have to still draw the rest. So this is Q1 minus Q2. Okay, and now what about here? I want to, for the composite engine, I want to draw an arrow which is pointing down. Okay, so if I do it this way, remember here, the sign convention is kind of absorbed into the direction of all these arrows. So if I want to do it this way still, then my Q1 has to be positive. And then this direction, if I draw a downward arrow, this has to take a minus sign. So this will be a Q1 minus Q2. Okay, so just imagine this to be a single reservoir for the composite engine. Okay, so this is now a real disaster, because now this is work, right? So I take all the heat energy and 100% convert this to work, and this is not allowed. And this is essentially not K. Okay, so I've shown you if you start from not C, if you try to play some trick and come up with some operations, they are not allowed, right? They are allowed. So I'm always allowed to do this. I have a normal engine. I can always plug it next to my any engine I want, and I can look at all these procedures. And then it will lead me to conclude that this is equivalent to having a not K. Okay, so this is the statement here. All right, so in the exercise, you need to do not K lead to not C. Okay, this is interesting. You need to think a little bit about this direction. In the past, I saw some answer which is very strange. I would tell you there is no y1. So here you see to come from here to here, I talk a lot, right? I use a lot of words to describe this. And that's to say, if I ask you to do this in your assignment, or if you read a textbook, you see a few lines of sentences. And then it's not quite easy for you to decompose this into this. Okay, so this is not the answer I want when I ask you to do number 2. You need to come up with a different arrangement. You need to draw it creatively for you to eventually arrive at this direction. So it's not easy to reverse engineer what I just say. For example, you decompose this, you add Q2, and this is a bit strange. Okay. Now, there are better way to handle this, and that is something, this is a task for you. Okay. All right, so this is the simplest which we will deal with. And we are going to look at a more complicated situation today. Okay. All right, so now let's look at this business of efficiency. Okay, efficiency of a heat engine. Last time I told you we can define the efficiency of a heat engine like this. Okay, so we can have now efficiency is defined at what you get divided by what you need to pay. So this Q1 is associated with this theta 1. Okay, so maybe I put this picture here just to remind you what is 1, what is 2. Okay, so this is a typical heat engine. This is Q1, this is Q2. And what we want now is to really ask about the question of efficiency. We are going to introduce this, we already introduced this concept, and we are going to use it a lot today. Okay, so this is, if you use the first law, that's to say, if you express W as the difference between the Q's, you can quickly obtain this result, Q1. Okay, so efficiency is 1 minus Q2 over Q1. Now, in thermodynamics, in this part of the course, this ratio is a very important quantity to investigate more. Okay, so now I want to do something a little bit specific, which is to say it's not as general as what we have discussed now. So again, what kind of specific ingredient I can introduce here? So what I would do is I'm going to consider a Carnot engine, again, a Carnot engine. Be careful of the wording, with ideal gas, with an ideal gas as the working substance. Okay, why do I want to do that? Because last week we already make some progress with this. Okay, so let me get this figure out. This is what I want. We talked about this last time, and we can use this to make very concrete prediction. Now, remember the M. Let me emphasize this. My M is to get this ratio. This ratio here. This ratio. Okay, so this is one thing. Keep in mind what I'm trying to get. And then the other thing which I should also remind you, in case you forget, is now this is always, this ratio is always positive. Okay, that is to say we already ignore our sign convention. If you want to make all this equation self-consistent, we better put the absolute sign. Okay, at least you should remind yourself that I'm really talking about the absolute sign. Otherwise, this will become a negative number, right? If I really respect the sign convention, when I as the one when I introduced the first law, this will have different sign, because one will describe heat and entering the system, the other one will be heat leaving the system. So there will be a -1 here. So when we define all this efficiency for the engine in all the textbooks, I recommend they all have this equation. And what you really should keep in mind is the fact that we are talking about the absolute value. Okay, and in this case, when you look at this picture, everything will become clear. Okay, when heat enter the system, you should in your mind automatically understand that if I really want to do the calculation based on first law, I should really take care of the sign convention by referring to the diagram. Okay, so I think this is okay. In the past, not too much confusion. Assuming you you follow all these videos and the lecture. Okay, so now let me do something a little bit more concrete to extract this ratio. Okay, and later I'm going to do it in a more general way to again extract this ratio. I'm going to do it 3 times for you today. Okay, okay, 1. Let's do it using the brute force method. Okay, if I run the cycle this way, if I run from A to B and then back to A, and I know and when I go from A to B, I have at A to B is dotted line, so this is isothermal. So this is isothermal expansion. Okay, and you know in this case your Q1. Okay, now your Q1 really this is defined with the sign convention we defined earlier, and this is the exercise you did before. Okay, so just sorry, this is one more again as usual. So if I take 1 mole of ideal gas as the working substance, you calculated this result. Q1, the heat entering the system, is R times the temperature at which the heat is supplied, times the log of final volume divided by the initial volume. Okay, let's check. We already checked before, but it's always useful to check. Now, how do I get this expression? You did it before, so let me very quickly remind you how we did it. It's an isothermal expansion of an ideal gas. Remember, this is only the ideal gas. And because this is an ideal gas, I have my internal temperature, I have the internal energy, which is only a function of temperature. So if the temperature does not change, du doesn't change, then I can write dq, d bar q is minus d bar w. We did it before. And for PV system, we know how to deal with d bar w, and that is the end result. Okay, a few lines of reasoning to get to here. Okay, this is the first thing. And the second thing, Q1 is related to this ratio, right? The log of this ratio. So VB is larger. This is an expansion. VB is larger. And this one is, VB is larger than VA. So this is greater than 1. So this is a positive number. So heat enter the system. Heat enter the thermodynamic system. Okay. All right. And then B to C is adiabatic expansion. So B to C, you see the volume continue to increase. So this is an expansion. And what we have now is, you see B is at temperature theta 1, C is at temperature theta 2. And in this case, we can show that this ratio is related to the ratio of volume like this. Okay, gamma minus 1. Okay, how do you get this result? So I will quote the result and you can convince yourself. For an adiabatic case, we already showed this is again not something you have never seen before. So we show something like this, right? We show that TV of gamma minus 1 is a constant for an adiabatic change. Okay, so I have temperature. Theta 1 is associated with B. So theta 1 times VB is raised to the gamma minus 1 is a constant. Okay, and gamma is the adiabatic index, just in case. Adiabatic index. Okay, now I'm bored. I will just write the result quickly. So I go from C to D now. C to D is isothermal compression. So I will be able to write down the expression for Q2. Theta 2 log of so C to D, right? So C to D. So I will have C to D like this. Okay, now D is smaller. Volume of D is smaller. So this is the opposite of this. So this is again correct. So heat will leave the system. Okay. And finally, we have D to A. D to A is the same as this. So let me write this again. And you need all this for you to work out this ratio. Okay. Okay, so if you use all this, result, you complete a cycle, right? And now I ask you what is the ratio, right? So you can kind of see how to do this, right? If you take Q2 divided by Q1, you will have a temperature ratio entering, and then you have all these volume ratios, which you will be able to recast into temperature ratios. Okay, so the end result is you have Q2 divided by Q1. And now, when you do it like this, you respect the sign convention. So if you then take everything to be the absolute value, what you will see is this result. Okay, so this temperature is always positive, right? So once you do it this way, you will have some minus sign lurking around, but if you are careful, you get this result. And this result is very important. Okay. We use the really, this is a very detailed way to really analyzing all these thermodynamic processes to get to this point. Okay, that's to say you should really appreciate this a little bit, right? Measuring heat flow is not that easy. I have a machine. I ask you how much heat transfer I will get from the reservoir to the engine. That is not something which is that easy to measure. Okay, and likewise, I ask you how much heat you reject, how much heat energy you reject to the river, for example. You say, well, I don't know. This is not that easy for me either. Okay, but if I ask you, tell me the ratio, and then you do know how to do it. You go to, for example, if this is a river and you have some big machine that you need to cool, you can go and measure the operating temperatures and the river and the temperature of the river. And that allows you to tell me the ratio. You might not know the individual Q2, you don't know the individual Q1, but you can tell me the ratio. And that's all I care. Because then you can answer the question. Right? if the engineer wants to know the performance of the heat engine, this is what he cares, right? So you will be able to so of course the next line is, if I know the temperatures of the reservoir, this is the result. Okay, the efficiency is simply given by this. Okay, this is important ratio, so we should try to look at it again. Okay, what do you mean? What do I mean? I want to give you another treatment. So remember this result. Okay, the ratio of the heat flow is equivalent to the ratio of the temperatures. So let me add one more. Okay, now let me push a bit more and use a treatment which I hope you like. Okay, so I'm going to talk about an ideal gas again. And this is more powerful for an ideal gas. Okay, we were talking about the ideal gas. Let me push a little bit deeper and talk about the ideal gas again. So now I want to get the same result for you differently, without going through all this nasty expression, without all this. Okay, how am I going to do this? This one, you can you still have a few lines to go through before you can get this result. Okay, we are going to do it with a little bit more insight. Sorry, this. Okay, where's the? Okay, this is crazy. Where's my Okay, let me do this again. So for an ideal gas, I will look at first law. Okay, so I'm going to look at the first law like this. So I'm going to write du is d bar q plus d bar w and apply it on an ideal gas. So I'm going to look at this. I'm going to, I will do it slowly. I'm going to change the subject like this. Okay, just rearranging. And I'm going to divide both sides by temperature. Okay, and now you know how to deal with this. So for a PV system, which is reversible, so for the PV system, I know how to deal with this. So I will have a plus, the work done can be written like this. Okay. Okay, and now next line is I will now I will use the result of an ideal gas. So ideal gas, because of an ideal gas. Now one mole of ideal gas. This can be further manipulated. So I would write it like this. I would write 1 over theta. So I will do this a little bit differently. I will write this as du d theta times d theta. Okay, I will explain this more. And the second term, I will use the equation of state of an ideal gas. Okay, so if I have a pressure divided by temperature, what I get is gas constant divided by volume, right? Okay, now let's look at this carefully. On the right hand side, okay, this one is easy. Okay, let me explain a little bit more what I'm trying to achieve here. Okay, first I can write it this way without a problem, right? This is just simply the change of variable, but it's not surprising to you that I use the total derivative rather than partial derivative. Okay, so this is easy. The fact that I can write this term as the total derivative is because I know for an ideal gas, U is a function of temperature only. So U is a function of theta only. And theta is my notation for temperature for the time being. Okay. So if you look at here, if you look from here to here, this coefficient in front of theta is only a function of temperature. Okay, whatever that goes into here is only a function of temperature. Temperature is a function of temperature. U is a function of temperature. I take derivative, it will maybe a function of temperature, but it cannot be a function of something else. So this is a function of temperature only, this product. And gas constant is a constant, and this whole thing is a function of volume only. Okay. It's not a function of volume times something else. Right? This really is only a function of volume, and this really is a function of temperature only. Okay. And now let's use our knowledge of function of state. So both temperature and volume are function of state. Okay, so if you go and integrate this right-hand side, if you integrate the right-hand side for a closed path, you have to get 0. Right? Understand this? This is a function of volume only. So this whole thing, if you take an integration for a closed path, you get 0, which means this whole thing can only depends on the endpoint. Okay. So we manipulate this in such a way that allows us to write this. But of course, the left-hand side is the same as the right-hand side. We get this result. Okay. I should remind you that this treatment is nice. This treatment comes from steam. I would let's see if I can get you the page number. Wait a minute. It's page 95. So this is page 95. So see steam. Page 95. Okay, but this is really a special case of a much general theorem, which we will also develop later, and that is a special case, a smaller version of closest theorem, if you like, because we are only talking about a very simple case, a very generic case. Okay, another thing you should keep in mind is this is for a reversible cycle. Okay, it's rather restricted, reversible PV and ideal gas. Now, just in case, why do we need this reversibility? Which part of the analysis tells you must have reversibility? Do you know? I get from this point to this point. The reason I can get from here to here is this is a reversible cycle. So there's one key part that requires me to invoke reversibility. So which part? You have the chat, so you can write to me, and then that allows me to test your understanding. No, right now I haven't assumed anything about the cycle. Right? That is what I'm going to apply. I didn't say anything about Carnot cycle. Guys, be careful. I talk about Carnot cycle here. I get you this result. Now I want to get you this result again for the Carnot cycle. Okay, for the Carnot cycle, be careful. So I develop something else. Then the next step is I will apply to a Carnot cycle. So up to this point, I say nothing about Carnot cycle. Okay, now the key is here. If you don't have reversibility, you cannot write this d bar w as p times dv. So this is in my note. I think I have 2 slides. Okay. Now, if this is not reversible, it means the easiest way is to understand that there's a friction. Imagine for the PV system modeled by the piston cylinder. Okay, so if you don't have if you have friction built in, you don't have reversibility, and you cannot relate the work done to the internal to the pressure of the gas, because all you know is the force on the piston, right? You push the piston, but because of the friction, you have some loss, and you don't know the loss. So you know how you can calculate the work done based on the force you apply on the piston, but that is not necessarily the same as this P, which is the pressure of the ideal gas. Okay, so the reversibility allows you to go from this to here. Okay, all right, now we can apply it to Carnot cycle. Okay, so now I will copy. Okay, I basically want this last line here. Okay, so I want to apply. Now apply what we learned. Apply this result to Carnot cycle. Again, this is a Carnot cycle based on ideal gas. Otherwise, I cannot apply this line, right? I derive this from an ideal gas and also a PV system. And the ideal gas is a substance, and the work, mechanical work, is performed by a PDV term. Okay, what do I have? So I just calculate this, right? Okay, so I will just draw quickly, it's faster. This is Q1 engine, Q2 theta 2, and work. Okay, so for my Carnot cycle, I have four segments. So let's look at A to B. A to B is the isothermal expansion. Okay, so if the segment is small enough, I can just look at this as the heat input, right? So I will have some heat input, Q1 entering the system at theta 1. Okay, so this is the isothermal expansion. So this is referring to my diagram earlier. So this will be A to B. Okay, so this Carnot cycle diagram. Then the adiabatic segment, there's no heat exchange, so debug Q is 0. Just write 0. And then the next line is you will have heat isothermal compression. So heat will leave the system. So you have Q2, and it leaves the system. You can think of it as it exchange heat with the reservoir at this temperature. All right. Now this, we better be careful with the sign convention again. So I'm going to enforce it. I'm going to call this really this is a heat enter a system. So this positive makes sense, and this is heat leaving the system. So I will force it like this. Okay, and then I will have the last segment, which is adiabatic again, and all this. What I've written is really this thing. I just go around and do accounting. I count how much heat energy I have exchanged, and then I look at my environment temperature, which is essentially what I'm doing here. Okay, and all this has to be summed to 0. Okay, and now with all this care, you can already see the result. So this is Q1 theta 2 theta 1. This is the same as Q2 theta 2. So I get this result. Now I can get it a lot quicker, but I spend time to explain thing to you. And if you rearrange, you get this result, this famous result. Okay. So this is the same result based on an ideal guess. I didn't do much calculation. You see, I didn't go through this messy calculation, and I get this based on my thermodynamic reasoning. I only need the first law, and I know a little bit about engine. I know my first law. I know the functional states, the mathematical structure of this, and then I can get this result. Okay. Now to help you with your revision, I will write a bit more. So this is C to D. This is isothermal. So this is adiabatic. So let's choose a different color, green. So this is D to A. This is B to C. Okay, the green color is adiabatic. Okay. Okay, one last thing I want to say about the Carnot cycle, and then we can take a break, is this. I don't know why all the slides are a bit messed up now. So let me add one more slide here. So this is about still about Carnot engine. So on the PV, we have this graph. We have an isothermal line drawn by the adiabatic, right? So this is my very ugly diagram. This is A, B, C, D. Okay, so AB is isothermal. AB and CD. Okay, so I would, for future reference, this is a good point to give you another piece of information. I can also choose to describe all these processes using different variables. So now my thermodynamic coordinates are pressure and volume. I can also choose different things. So for example, I can choose theta, which is the temperature. So this is my temperature. And I will describe it, the same process on theta S or TS diagram. So this S is not yet introduced properly, but you know the meaning already. This is the entropy. Okay, I'm going to draw this for you, and then keep this in mind. We will be able to use it in the future. Okay, so for the isothermal process, this is particularly simple. That's why I want to say it now. Okay, isothermal, so temperature cannot change. So suppose this is theta 1, this is theta 2. Right, so this will be theta 1, right? High temperature. You have isothermal expansion at higher temperature. So this will be your theta 1. It will just be a horizontal line. So this is the process A to B, isothermal. And it turns out that for the adiabatic segment, B to C, on the TS diagram, this is also particularly simple. This is another straight line. So B to C, this is a process that happens at the same entropy. So the entropy change from here to here is 0. Okay, and now you know how to complete the picture. You just get a very beautiful rectangle. So this is D and this is C. So if you run A, B, C, D, A, this will be like this, A, B, C, D, A. Okay, and this is and the heat flow. Let me label it too. So this is Q1 entering the system, and this is Q2 leaving the system. Okay, now I already told you, if you know all this expression, you have a very good way to calculate the work done, right? So this work done is related to the area, PDV. Okay, and now my question for you, you don't need to answer now, but do keep this in mind, this question in mind, is what is this area enclosed? Here I can define some area when I go through this path from A, B, C, D, A, right? So this is A, B, back to A. And likewise, this is A, B, C, D, A. And what is the meaning of this thing? Okay, so what is the meaning of this integral? Okay, let's take a break. And after the break, we will talk about Carnot theorem, which has to do with the efficiency. Okay. All right. So now is now come back in about 10 minutes. So come back at 1:35. Hello, welcome back. Okay, let's move on to to look at Carnot's theorem. So this is, if you like, this is yet another statement of the second law, but now is formulated in terms of efficiency. Okay, so these are all related. Okay, let me first state about this theorem. So before the break, we really look into this issue of efficiency, right? We use it to get some prediction. That's to say, if you know the temperature of the reservoir, you can say something. And if the working substance is an ideal gas, the efficiency can be very easily written in terms of the temperature of the reservoir. Okay, so now now you know there's something called the efficiency, and you might want to ask yourself, is there a way to really get a very, very efficient engine? And if so, what is the limit? What is the maximum efficiency one can get? One can design a machine to do this. Okay, so there's to say, if you one day if you go to the shop and buy a machine, if the machine claims some kind of efficiency which is higher than the efficiency of a Carnot engine operating between the same reservoirs. Let's say you buy an engine, you're going to operate this engine between the same reservoirs, and if the product description say the efficiency is higher than the efficiency of a Carnot engine operating between the same two reservoirs, you better don't buy that product, because this violates the second law of thermodynamics. Okay, so let me put this in words for you. So Carnot's theorem, tells you no engine operating between two given reservoir can be more efficient than a Carnot engine. So this Carnot engine we have been learning and playing with is the most efficient engine you can get. Okay, operating between the same two reservoir. Okay, so you get this point. So this you spend some time to look at this, so you know what we are heading to. Okay, that is in simple word. If I have two reservoir, the most efficient engine I can construct is the one based on a Carnot cycle. Okay, so let's try to prove this. This is kind of fun to do. And the way to do this is, again, very similar in spirit. So I'm going to assume we are going to do something like this. We are going to assume there's some engine which is hypothetical, right? We know it's not allowed. So I'm going to do this symbol first, assume this engine and hypothetical engine, which is more efficient, which is more efficient than the Carnot, than the Carnot engine. So I'm going to use symbol CN. Okay, this is the hypothetical. This is a Carnot. If you read my note, I use try to use the same symbol, same wordings. Okay, so you can you will be able to find the meaning. That is to say, I assume again. I assume. What is my assumption? I assume this: the efficiency of a hypothetical engine is greater than the efficiency of a Carnot cycle. Okay, and let's put some diagram now. So here we go. That's again very standard way to prove. This is my hypothetical engine. So this is my hypothetical engine. So I will do CN first. Okay, so the hypothetical one, I would just take this one here. I need this picture, so later. Okay, and you can see I'm trying to what I will try to do later. Okay, let's just look at them individually. So this is the edge hypothetical, and label everything. Okay, so this is Q1. For this hypothetical engine, so this takes Q1H. Okay, so this is a heat from the hot reservoir, heat flow from the cold reservoir, heat flow to the cold reservoir. So this is hypothetical H2. Okay, so 2, 1. And then this engine, give me some work, WH. Okay, no complaint, right? This is just really labeling everything. I'm going to do the same here. So I'm going to label this one is Q CN1, but then it's too messy. So I will just call QC1. And this is QC2. And this is some heat, right? This is a very standard engine. Right now they look the same, right? It's just a different symbol. Okay, so let's look at them differently and then individually and write a few equations. So what can we write? We will write, we will start from our assumption. Okay, so this is our assumption. The efficiency of this engine is, the hypothetical engine is larger than the efficiency of the Carnot engine. Okay, and then the efficiency of efficiency is defined as the work you can extract divided by the input, heat energy input. Okay, so this is the definition we learned earlier today. Okay, let's just write this down and copy this. So this is a heat, sorry, this has to take a C here. Okay, so this is WC divided by QC1. Okay, this is the definition. This is by definition, Okay, now we do first law. So first law tells you I can write WH is what I try to give to the engine minus what I have to waste. Okay. And likewise for the other one, WC. I have C1 minus QC2. Okay, so right now, really just very carefully write everything down without doing much. Okay, now here is the key. Here is the key. I draw these two diagrams, but something special about the left-hand diagram, which I can use. Do you want to guess? Now, I look at this diagram. If you haven't seen the note, you can maybe guess a little bit. It's fun. I basically draw two identical engines, but there's one special property of the Carnot engine which I can use. What is that? Excellent. I can use the property that this engine is reversible, right? So the CN, the one on the left, is reversible. So let me drive it backward. So I don't want to mess up this. I will drive it backward for you. So now I'm going to drive this backward. I don't want to draw it again. So please just give me your attention. So I'm going to drive. Sorry. This is an eraser that is going to erase everything. I'm going to drive the one on the left backward because this engine is strictly reversible. So I can drive it backward by simply flipping all the direction of the arrows, right? You agree, right? So I'm going to do, this is now, originally this is down. This is down. So I'm going to, after flipping, I will use a different color. I use this. Okay, so pay attention. I'm going to drive it backward. So this is the backward arrangement. Okay, and I have to do the same with this one. So all the arrows, I just flip the direction. Originally, this is going from the engine. So now I want to arrange it to go into the engine. Okay, so I would draw it like this. It has to go into the engine. Happy? Right? I just drive it backwards. So now here, actually, I have this picture. This is a sequence of event that you can. Okay, I copy the slide. This big paper is getting a bit crazy today. The slide is somewhere else. Anyway, I have the sequence of event for you. You can when you revise, you see everything. So now I use the fact that Carnot engine is reversible. Okay, and the next thing I want to do is a standard trick now. Now, if I have an engine which is reversible, I need to supply some work because now this arrow is flowing into the engine. I need to supply some work. And then I look at my diagram, I suddenly have an idea. Why don't we use this output, the work energy output, to drive the Carnot engine? I can always do that. As I say, I can adjust the rate of this engine such that this is the required, the amount we want. Okay, so what I would then do is really drive it like this. So this is a sequence of event, which I hope if you watch the video, you will be able to follow. So that is what I want to do, right? I take the output from H and feed it into the Carnot engine. Okay, so let me write down the equation. Okay, so I have here, I will have this result. This result means I will, after I invoke the reversibility, I also demand WH to be the same as WC. Okay. All right, so what do we see now? Now, as a standard trick, we can analyze what happens now. So be very careful with all this logic. So what I have, let me label this. So this is what we assume. By definition, we assume this to begin with. So by definition, I have this. So this is simple. This is from 2 and 3 are from first law, and 4 is after I reverse the engine, I do something like this. Okay, I demand this to be the same. So because of 4, I can say something else, right? Because of this equality, if I look at 1, now WH and WC are the same. I can cancel from both sides. After all this remains the same. Okay, even if I drive the Carnot engine backward. Okay, so I can go back and conclude that I must have QC1. So I go to my inequality. My QC1 has to be greater than QH1. Okay, so this is because of 4. Okay, after I have 4, I can revisit 1 and I conclude this. And because of 4, and obviously 2 and 3, I can also revisit, right? I revisit 2 and 3. I can write QC1 minus QC2 is the same as QH1 minus QH2. Right? These two are equal. These two are equal, so this must be the same as this. Okay. Now let me play a little bit with this. I'm going to now everything is just simple, so it's easy to follow. You will see why I want to do things like this. Now I want to group everything associated with the hot reservoir. That's to say, everything with the index 1, I want to group together. So that is to say, I would like to have QC1 minus QH1. I group together on one side of the equation. And then everything with cold reservoir, I move to the other side. So I have QC2 minus QH2. Okay. But I can say more about this, right? Because QC1 is greater than QH1. So QC1 minus QH1 has to be a positive number. And since this is the same as this, I can conclude that this difference is greater than 0, and this difference is also greater than 0. Okay, and you might wonder why do I do this? That's because I want to reconstruct my composite engine. So I need some manipulation for me to correctly draw this engine. So now I'm going to draw this engine based on all the information so far. So maybe logically you should read from this to here and then like this to here. Okay. So when you revise this, sorry. Okay, like this. Okay. Okay, let's draw it. What information do I have now? So as far as now I do the composite engine, right? So in this case, after I look at the composite engine, this becomes internal, so I don't need to draw them anymore. Okay, so now why do I care about this sign? That is because it depends on how I draw the direction of the arrow. Okay, if I want to draw this arrow to be upward, okay, so if I want to draw this to be the upward, so I need to come here and look at this. The sign convention, as I mentioned many times, is absorbed into the direction of the arrow. So if I call this direction up, this is the same direction as QC2. Okay, so if I want to represent QH2 on this diagram, it has to take a minus sign. Okay, so if I have the composite engine to worry about, I will have two components to include. Okay, so now I will include QC2 plus this one, which is minus QH2. Okay, so I will have QC2, assuming this is up, I have to do it like this, minus QH2. Okay, and then why do I need to be careful? Because if this product is negative, then it means I have to flip the arrow again. You get this point? But this, sorry, I say the product, this difference. But now this difference, this QC2 minus QH2 is positive. So that's okay. So this is allowed. I can draw it upward. Okay, and likewise, I have another one to worry about. I have QC1 and QH1. So QC1 minus QH1, okay, I say it the other way. QC1 minus QS1 is the positive number. So if I want this arrow to be like this, up, it has to have the same sign as QC1. Okay, so this will be QC1 minus QH1. Okay, and now you know the problem. This is a not C. This is a machine which violates the closest theorem, closest statement. Okay, what can you conclude? What you can conclude is this. So the conclusion from this work is this. I'm going to write here small. So you assume this to begin with. You assume this to begin with. And then you manipulate all this engine. You realize this will lead you to a violation of the closest engine. So you know this is not allowed by second law. So this cannot be true. Okay, and therefore what you can only say is the hypothetical engine can at most be as efficient as the Carnot engine. You cannot be more efficient than that, but you can be less efficient than the Carnot engine. You can be as efficient as the Carnot engine. That's okay. Okay, so that is the statement. Okay. And now this is really the next part. Is really the heart of this whole thing. So if further, I know that H is also reversible. Right? Up to now, up to this line, I didn't say anything about whether H is reversible. But if H is also reversible, I think you can convince yourself that you will be able to construct the argument to show something like this. You can also show that if H is reversible, the hypothetical engine can be more efficient than the Carnot cycle. Okay. Right now, this is where people will complain. Okay, this complaint comes from the fact that you say, you already say that Carnot engine is the most efficient. How can your hypothetical engine be more efficient? This misunderstanding comes from the fact that this is an additional requirement, which means you have to satisfy this and this one at the same time. Okay, so you have these two. So that is to say, therefore, you have these requirement plus this requirement. Okay, so don't complain about this. Okay, just make sure you understand. And to simultaneously satisfy these two, you can only conclude that the efficiency must be the same. Okay, so this is a statement. Okay, the statement is this: all reversible engines operating between the same two reservoirs are as efficient as a Carnot engine operating between the same two reservoirs. Okay. All right, there's a typo. What is the typo?
The typo is in the composite engine, the pointing upward into the reservoir one. It should be QC1 minus QX1.
Sorry, a bit too fast.
The composite engine.
Is it this slide or something else?
Just this slide. Yeah.
This slide, yes.
The engine.
Engine.
Composite
Yes.
engine. Yeah. Yes. The QC1 minus QX1.
Ah, okay. Thank you. This one right here.
Yeah.
This one. Sorry, this is a typo. Okay. This is one. Okay. Happy? Fixed, right? Okay. Thank you, Mr. B19. Okay, excellent. There's a question. Now, if H is reversible, the hypothetical engine is also reversible, how do I get this line? Okay, I say you can arrange the proof for you to reach this result. Right? How do you get this? Actually, you are the same student who talk about reversibility. Now, anyone wants to quickly explain this? The picture, the key picture is this. Now you see. Okay. If H is reversible, I can choose not to reverse this engine. I can reverse this. Then I get the opposite result. Yes, thank you. Okay, but be careful. That is to say, I need to do this step twice. Okay, so whether or not this is reversible, I will have this first result. Okay, and then the second part is I take the same diagram. Now I reverse the other engine. Okay, now you get it. I don't know whether others are happy or not. Okay, so this is an additional requirement that you get. Okay. All right. Okay. Thank you again, student Thai. Thank you for the question. All right. Next. This is about the thermodynamic temperature. Now we are really in the position to do this statement, to try to define the temperature. Now, 2 weeks ago, I told you when we have the zeroth law, I told you we only established that there's something called the temperature. So we call that the empirical temperature. And that is a quantity which is important when you have thermodynamic equilibrium. So when you have thermodynamic equilibrium, the temperature, there's a quantity which is a constant, and that quantity we might as well call it the temperature. And how do we really define it? And this is when you can do it. Okay, and in my note, I say there's a good way to do that, and that's using the Carnot engine. And this is we are in a good position to do that now. Okay, so this rely on this fact. So we can define a temperature scale. Okay, the point is we want to define a temperature scale which does not appeal to any physical system. I say we can use Carnot cycle, but I do not really want to demand, for example, using a particular substance. I just want a Carnot engine. Okay, I don't necessarily want to put the ideal gas. I put the ideal gas earlier to get the result quickly. But in the end, the point is once you do the Carnot cycle, use the Carnot cycle to define the thermodynamic temperature, you will find that this is essentially the same as the Kelvin temperature scale based on the ideal gas. Okay, again, as usual with all this part of the course, be careful of all the logic. Okay, now we just say something like this. I didn't write it down, but this is what we need. So what we want to say is all reversible engines operating between a given pair of reservoir. This is R. Are equally efficient. This is what we just showed 5 minutes ago. Are equally efficient. Okay, so the efficiency, when you do the efficiency formula, you know this efficiency formula depends on, so let's say the reservoir is labeled by A and B. The efficiency has this dependence on Q1 or QA and QB. Okay, right? Remember this, right? We did it this morning. Sorry, we did it just before the break. Efficiency is 1 minus the heat ratio. Heat ratio. Okay. So this is from the engine point of view, this is what you care. But if you think a little bit deeper, this heat transfer comes from the reservoir. Okay, so the reservoirs. And how do I label the reservoir? And up to now, you see my label for the reservoir is using theta 1, theta 2, and so on. So the reservoir are labeled, or you can also say they are characterized by some temperature, right? Okay, I know I have a reservoir. I didn't tell you anything else about the reservoir except the temperature. This is a reservoir. I didn't tell you what is the size, what is the mass, what is the material. I only told you this is a reservoir at theta A, and therefore the efficiency, this one, I run the engine between a given pair of reservoir. Right now, you look at this statement again. Right, I know the engine is operating between a given pair of reservoir, which means if I want to characterize the efficiency, this efficiency has to be depending only on the property of the reservoir, right? If I plug in another reversible engine, and this engine can be very complicated, the only thing I know is this engine is reversible. I plug it between a set of reservoirs, and it magically turns out to have the same efficiency. Okay, that is to say the efficiency can only depends on the property of the reservoir. And this property is labeled by theta A and theta B. And therefore the efficiency can only be a function of theta A and theta B. Okay. And efficiency has this factor. And therefore I can write this line. Okay, so now let's draw a few pictures and repeat the same thing again, but in a slightly different way. So I'm going to, all reversible engines are equally efficient, and they are as efficient as a Carnot engine. So I might as well use a Carnot engine. Okay, and this reversibility, you can also say they are all effectively the Carnot engine, because they are reversible and they are operating between a given pair of reservoir. Okay, so this statement is really protected by Carnot's theorem. All right, so let me put some heat flow again. So this is 1 and this is 2, okay, and I get some heat out. So this heat is sorry, I get some work done. Okay, this is Carnot engine 1, and then I'm going to dump it into theta 2. All right, so now you imagine I connect another Carnot engine like this. Okay, now this becomes the hot reservoir of the second Carnot engine. So I can also extract heat from here. And this is a Carnot engine 2. And then I need to dump some heat into theta 3. And this is Q3. Okay, and you already know that I have the freedom to run this in a way that the heat I extract is the same as the heat input. Okay, I have a way to configure this engine this way. So I can write this as theta Q2. Okay, and then I will extract some work W2. Okay, so now I let me look at the top engine C1. So for C1, I will have Q1 divided by Q2. This is the same argument as before. I will have this as a function of theta 1 and theta 2. Okay, now you just imagine I copy this engine and put it here, and they are equally efficient. Okay, so they are Carnot engine. So I can also write Q2 divided by Q3. And that has to be depending only on the property of the reservoir. I don't know why it's F. I don't care. I just know that can only depends on this independent variable labeling the reservoirs. Okay, and now the standard trick is again to look at a black box, which is a composite engine. Composite engine like this. I will call this composite engine C3 or C. Okay, and in this case, this engine only see Q1 and Q3. So I will have Q1 and Q3. And this can only be a function of temperature of the reservoir. Okay, now if you look at this, you will see to get this result, Q1 divided by Q3, I can multiply these two. So if I multiply Q1, the two expression in green color, I will get the one in purple. Okay, so that is to say I am forced to write something like this. I can write this times this is the same as this. Okay. No, sorry. Okay, you have seen this before. On the right hand side, this is only a function of theta 1 and theta 3. And on the left hand side, magically you have theta 2. How is it possible? So this theta 2 has to cancel. Okay, so this one has to cancel because there's no dependence on theta 2. Okay, so to do that, to cancel theta 2, you have to you can write this function as some kind of ratio which is completely separable. So the top will be only a function of theta 1, and the bottom, the denominator, is only a function of theta 2. Okay, so if you define it this way, you'll be able to you'll be able to reconcile this line here. Okay, And if I do it this way, I might as well call this temperature 1 and temperature 2. Okay. So to conclude, now this function g is proportional to T1, and there's no more offset anymore. If you have an offset, you cannot really cancel it. So there will be a proportionality constant which will cancel, and then you can go on and do your usual calibration, and you get a temperature scale. And this temperature scale defined by this Carnot engine trick is called the thermodynamic temperature. Okay, and this turns out to be the same as the Kelvin scale we defined earlier using the ideal gas, because back then we write it like this. And we write it like this, right? But this really takes the meaning of Kelvin scale, right? You know before, this is Kelvin scale, and this is the same, equivalent to Kelvin scale, right? So I can write this treatment allows me to now finally write this efficiency as the difference between the ratio between the temperature of the reservoir, defined using the Kelvin scale. Okay, another way to write this is this Q2 divided by Q1 again is the same as